Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why space looks black. When astronauts look out the windows of the International Space Station, they see a view that never fails to inspire awe. Earth below with its blue oceans and swirling white clouds, and beyond it, the blackness of space dotted with brilliant points of starlight. That darkness seems natural and expected. Space is far from the sun, far from Earth's atmosphere, so of course it's dark. But this simple explanation masks a puzzle that perplexed astronomers for centuries. If the universe is infinite and filled with stars in every direction, then no matter where you look, your line of sight should eventually hit a star. The entire sky should blaze with light, as bright as the surface of the sun in every direction. Yet space is dark. This contradiction, known as Olbers' paradox after the German astronomer who popularized it in the 19th century, reveals deep truths about the universe's nature, age, and evolution. The puzzle seemed straightforward to early astronomers. Imagine the universe extends forever in all directions, filled uniformly with stars. Draw an imaginary sphere around Earth at any distance. That sphere contains a certain number of stars. Now draw a larger sphere at twice the distance. This larger sphere has 4 times the surface area, so it contains 4 times as many stars. Each individual star appears fainter because it's farther away. Brightness decreases with the square of distance, but there are 4 times as many stars, exactly compensating for their individual faintness. Every shell at every distance contributes the same amount of light. If the universe is infinite, there are infinitely many such shells, so the total light should be infinite. The night sky should be blindingly bright. Clearly, this doesn't match what we observe. The night sky is dark except for individual stars, planets, and the faint band of the Milky Way. Something must be wrong with the reasoning. Early astronomers proposed various solutions. Perhaps dust between stars absorbs starlight, darkening distant regions. But this doesn't really solve the problem. The dust would heat up from absorbed starlight and would eventually glow just as brightly as the stars themselves. Perhaps stars aren't distributed uniformly, with empty voids creating dark patches. But if the universe is infinite and eternal, stars should exist everywhere eventually, filling in any voids given enough time. The true solution involves the universe's finite age and its expansion, concepts unknown when Olbers formulated his paradox. The universe is not infinitely old. It began roughly 14 billion years ago in the Big Bang. Light travels at a finite speed, so we can only see light from objects whose light has had time to reach us since the universe began. The observable universe has a boundary, not a physical edge, but a horizon beyond which we cannot see, because light from more distant regions hasn't had enough time to reach us yet. This finite light travel time alone would solve Olbers' paradox even if the universe weren't expanding. There simply aren't infinitely many stars visible, only those within about 14 billion light years, the distance light can travel in the age of the universe. This limits the total amount of starlight reaching us to a finite value, much less than would be needed to make the sky bright everywhere. But the universe's expansion adds another crucial element. Distant galaxies are receding from us as space itself expands. This recession causes their light to be redshifted, stretched to longer wavelengths. Light that left a distant galaxy as visible or ultraviolet radiation arrives, at Earth shifted into infrared or even microwave wavelengths. Our eyes cannot detect infrared or microwave light, so this redshifted radiation doesn't contribute to the visible brightness of the sky. The farther away a galaxy is, the faster it's receding, and the more severely its light is redshifted. The most distant galaxies we can observe have their visible light redshifted so far that it arrives as infrared or even radio waves. The cosmic microwave background radiation demonstrates this effect perfectly. This radiation, released when the universe was only about 380,000 years old, fills all of space uniformly. When it was emitted, it was visible an infrared light with a temperature of about 3,000 degrees. But in the billions of years since then, the universe has expanded by a factor of about 1,100. The wavelengths of this radiation have been stretched by the same factor, shifting what was once visible light into microwave wavelengths. The temperature corresponding to this radiation has dropped to less than 3 degrees above absolute zero. If we had eyes that could see microwaves, the sky would glow uniformly in every direction with this faint microwave light. But in visible light, it contributes nothing, leaving the sky dark. Another factor contributing to the darkness of space is the finite lifespan of stars and galaxies in their current bright state. Stars don't shine forever. They exhaust their fuel and fade. The universe's star formation rate was higher in the past and is declining now as gas is used up. In the far future, the universe will contain many more dead stellar remnants than active shining stars. Even if the universe were infinitely old, which it isn't, the sky might still be dark because most stars would have long since burned out. The darkness also depends on perspective. From Earth's surface, the atmosphere scatters sunlight, making the daytime sky bright blue and the nighttime sky somewhat illuminated by air glow and scattered artificial light. In space, without atmosphere to scatter light, the sky appears black in all directions, except where you're looking directly at a light source. Sunlight doesn't fill space with general brightness the way it illuminates Earth's atmosphere. Light travels in straight lines, and unless it's scattered or reflected by something, it remains invisible. You can be in bright sunlight in space, with the sun illuminating your spacecraft, but when you look away from the sun, you see only darkness and stars. The blackness of space also reveals something about the nature of light and vision. We see objects because they emit or reflect light into our eyes. Empty space contains no particles to scatter or reflect light, so there's nothing to see. It appears black. This is different from looking into a dark room on Earth, where at least some scattered light usually reveals dim shapes. Space between stars is truly empty of matter, with typically less than 1 atom per cubic centimetre. With so few particles to interact with light, the light simply passes through unaffected, leaving space black. Interstellar dust does exist, and it does affect starlight, but not enough to solve Olber's paradox. The dust absorbs and scatters light from stars behind it, causing extinction, making those stars appear fainter or invisible. This creates the dark dust lanes visible in photographs of the Milky Way and other galaxies. But the dust also glows faintly in infrared light from absorbed stellar radiation. The net effect is to redistribute light from visible to infrared wavelengths, not to eliminate it entirely. Even in regions with many visible stars, the spaces between them remain black. The Orion Nebula, one of the brightest nebulae visible to the naked eye, appears as a glowing cloud because gas in the nebula fluoresces in response to ultraviolet light from young hot stars within it. The gas absorbs ultraviolet light and re-emits it as visible light, making the nebula glow. But between the glowing gas clouds, space remains dark. Only where matter exists to interact with light does the light become visible. From certain perspectives, space isn't quite black. Sensitive instruments can detect faint glows from various sources. Zodiacal light, caused by sunlight reflecting off dust particles in the inner solar system, creates a faint glow along the ecliptic. Airglow from Earth's upper atmosphere creates a faint luminescence visible from orbit. The integrated starlight from billions of faint, unresolved stars creates a faint background glow called the extragalactic background light. But these glows are extraordinarily faint, thousands of times dimmer than the darkest sky visible from Earth's surface, and our eyes cannot detect them. To human vision, space appears black. The darkness of space has practical implications for astronomy. Because space is black, stars and other objects stand out clearly against the background without competing light washing them out. The best ground-based telescopes are built on remote mountaintops, far from city lights, precisely to take advantage of darker skies. But even the darkest Earth-based sight cannot match the blackness of space, where no atmosphere scatters light and where the sky is dark even in the direction of the sun. This darkness also affects spacecraft and astronaut safety. On the shadowed side of Earth or another planet, or in the shadow of the spacecraft itself, darkness is absolute, except for starlight. Astronauts working in shadow must use artificial lights because the starlight alone is far too faint to see by. The contrast between brilliant sunlight and deep shadow is extreme, creating challenges for cameras and human eyes trying to see details in both bright and dark areas simultaneously. The question of why space looks black connects to the deepest questions about the universe's structure and history. Space is dark because the universe had a beginning, because it's expanding, because light travels at a finite speed, and because stars have finite lifetimes. If any of these factors were different, if the universe were infinitely old and static, for instance, the sky would not be dark. The darkness itself is evidence for the Big Bang, for cosmic expansion, for the finite age of the universe. Every time you look up at the night sky and see darkness punctuated by stars rather than a uniform blaze of light, you're seeing direct evidence that the universe had a beginning, that it's been expanding for billions of years, stretching the light from distant sources into wavelengths your eyes cannot detect, leaving the spaces between stars as dark voids that reveal the fundamental nature of the cosmos through their very emptiness. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, This zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath the Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice, material that spacecraft have flown through and analyzed. The presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favourable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbor life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harboring biospheres in their hidden oceans. Binary star systems, where two stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from two suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets, and the basic ingredients for life, elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. How galaxies live and die. Galaxies are not eternal, unchanging structures frozen in the void. They are dynamic systems that evolve over billions of years, passing through distinct phases from birth to maturity to eventual decline. Each galaxy follows a life story shaped by gravity, star formation, gas flows, and violent interactions with other galaxies, ultimately transforming from active star-forming systems into quiet collections of aging stars, or sometimes meeting more dramatic fates in collisions that tear them apart and rebuild them into something new. The birth of a galaxy begins in the early universe, just a few 100 million years after the Big Bang. At this time, the cosmos was filled with vast clouds of hydrogen and helium, distributed nearly uniformly, but with tiny variations in density imprinted during the first moments after the Big Bang. Dark matter, invisible but gravitationally powerful, began to collapse first into clumps and filaments, creating gravitational wells that attracted normal matter. Gas flowed along these dark matter filaments, accumulating in regions where the gravitational pull was strongest. These early accumulations of gas were turbulent, chaotic places. The gas was cold, collapsing under its own gravity into smaller and smaller clumps. Within these collapsing clouds, the first stars ignited, massive and brilliant, burning through their nuclear fuel in just a few million years before exploding as supernova. These explosions enriched the surrounding gas with heavier elements, carbon, oxygen, iron, and others, that hadn't existed in the primordial universe. More stars formed from this enriched gas, creating a positive feedback cycle where star formation bred more star formation. A young galaxy is a vigorous place, forming stars at prodigious rates. Gas continues to fall into the galaxy from the surrounding cosmic web, providing fresh fuel for star formation. These early galaxies are often irregular in shape, lacking the elegant spiral arms or smooth elliptical forms of mature galaxies. They're clumpy and asymmetric, filled with giant regions of intense star formation where thousands of stars are being born simultaneously. The massive stars in these regions produce copious ultraviolet radiation that ionizes the surrounding gas, creating glowing nebulae visible across vast distances. As a galaxy matures, it begins to develop structure. If it has significant angular momentum, inherited from the rotation of the gas cloud from which it formed, it settles into a rotating disk. Within this disk, density waves organize stars and gas into spiral arms, elegant patterns that rotate around the galactic center. Stars form preferentially in these spiral arms, where gas is compressed by the passing density wave. The galaxy takes on the classic spiral form we see in galaxies like our own Milky Way or the nearby Andromeda galaxy. The disk of a spiral galaxy contains young hot blue stars mixed with older, cooler yellow and red stars. Gas lanes trace the spiral arms, visible as dark patches where dust blocks light from stars behind. At the center lies the bulge, a roughly spherical concentration of older stars, and at the very heart of the bulge lurks a supermassive black hole, containing millions to billions of times the mass of the Sun. This black hole profoundly influences the galaxy's evolution, though in ways that are still not completely understood. Star formation in a mature galaxy is a self-regulating process. Gas collapses to form stars, but the stars themselves affect the gas around them. Massive stars produce powerful winds that push gas away. Supernova explosions inject tremendous energy into the interstellar medium, heating gas and driving it outward in expanding bubbles and shells. This feedback can temporarily suppress star formation in regions around young star clusters, giving the galaxy a breathing, pulsating quality where star formation surges and ebbs over millions of years. The supermassive black hole at a galaxy's center can dramatically affect its evolution. When gas falls toward the black hole, it forms an accretion disk, heating to millions of degrees and emitting intense radiation across the electromagnetic spectrum. This active galactic nucleus can outshine all the stars in the galaxy combined. The energy released can drive powerful winds and jets that blow gas out of the galaxy entirely, removing the raw material needed for star formation. Many galaxies go through active phases when their central black holes are feeding vigorously, then quiet phases when little material is falling inward and the black hole lies dormant. Galaxies don't evolve in isolation. They're part of a cosmic web, connected by filaments of dark matter and gas to other galaxies nearby. Smaller galaxies fall into larger ones, adding their stars and gas to the growing giant. The Milky Way has consumed dozens of smaller satellite galaxies over its history, and it will consume more in the future. Each merger adds complexity to the galaxy's structure, sometimes triggering bursts of star formation as gas clouds collide and compress. sometimes disrupting the orderly rotation of the disk and scattering stars into less organized orbits. Major mergers, when two galaxies of comparable size collide, are transformative events. The collision unfolds over hundreds of millions of years as the galaxy's gravitational fields interact. Stars almost never collide directly. The distances between stars are so vast that even in a galactic collision, stellar collisions are extraordinarily rare. But the gravitational interactions between the passing galaxies create tidal forces that stretch and distort each galaxy's structure. Long tidal tails of stars and gas stream away from the collision site, some eventually falling back into the merged system, others dispersed into intergalactic space. The gas in colliding galaxies does collide, directly and violently. Giant molecular clouds slam together at speeds of hundreds of kilometers per second, creating shockwaves that compress the gas and trigger intense bursts of star formation. These starburst galaxies can form stars at rates hundreds of times higher than normal galaxies, converting much of their gas into stars within just tens of millions of years. The newly formed massive stars live brief lives and explode as supernovae, creating a cascade of feedback that heats the remaining gas and can drive much of it out of the galaxy entirely. The end result of a major merger is typically an elliptical galaxy. The orderly rotation of the spiral disks is destroyed by the chaotic gravitational interactions of the merger. Stars end up on random orbits, creating a roughly spherical or elliptical distribution rather than a flat disk. Elliptical galaxies contain mostly old stars, appearing yellowish or reddish because they lack the young blue stars that make spiral galaxies appear white or blue. They have little gas left for star formation, having either converted most of their gas into stars during the merger or expelled it through feedback from star formation and active galactic nuclei. Elliptical galaxies represent a kind of middle age or retirement for galaxies. They're massive, sometimes containing trillions of stars, but they're largely quiescent, forming few new stars. The stars within them are aging, slowly converting hydrogen to helium in their cores, gradually dimming as they exhaust their fuel. Over hundreds of billions of years, these stars will die one by one. Low-mass stars will swell into red giants, then shed their outer layers as planetary nebulae, leaving behind white dwarf remnants. Higher-mass stars will explode as supernova, leaving neutron stars, or black holes. As stars die, they return some of their material to the interstellar medium, but much of their mass remains locked in stellar remnants. The galaxy's gas supply dwindles, and with no new gas falling in from outside, star formation gradually ceases. The galaxy grows dimmer as its most luminous stars die and are not replaced. Eventually, in the far future, such a galaxy would consist primarily of white dwarfs, neutron stars, and black holes, the dead remnants of stars that once shone brightly. Some galaxies meet more dramatic ends. In dense galaxy clusters, high-speed collisions and gravitational interactions can tear galaxies apart. Ram pressure stripping occurs when a galaxy moves through the hot intracluster gas that fills the space between galaxies in a cluster. This hot gas, though tenuous, exerts pressure on the cold gas in the moving galaxy, stripping it away like wind pulling leaves from a tree. The galaxy is left with no gas for star formation, rapidly aging as its existing stars evolve and die without being replaced. Galaxies can also be tidally disrupted by close passes to much more massive galaxies. The tidal forces, the difference in gravitational pull between the near and far sides of the smaller galaxy, can be strong enough to overcome the galaxy's self-gravity, pulling it apart into streams of stars that wrap around the larger galaxy. The Milky Way is currently in the process of tidally disrupting the Sagittarius dwarf elliptical galaxy, a small galaxy that passed too close and is now being stretched into a stream of stars encircling our galaxy. In the very long term, Over timescales of trillions of years, galaxies face a dark future. The expansion of the universe, driven by dark energy, is accelerating. Galaxy clusters will remain gravitationally bound, but individual clusters will become increasingly isolated from each other as the space between them grows. Within each cluster, galaxies will gradually merge, forming ever larger elliptical galaxies. Eventually, each cluster will merge into a single giant elliptical galaxy containing all the matter that was once in dozens or hundreds of separate galaxies. Even these ultimate galaxies will fade. Star formation will cease entirely as all available gas is either converted into stars or expelled from galaxies. The remaining stars will age and die. White dwarfs will cool, becoming black dwarfs, cold, dark stellar remnants that no longer emit visible light. Neutron stars will radiate away their heat over inconceivable timescales. Black holes will slowly evaporate through Hawking radiation, though this process takes vastly longer than the current age of the universe. 10 to the power of 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 10 to 100th power years for a solar mass black hole, far longer for the supermassive black holes, at galaxy centers. The life cycle of galaxies is intimately connected to the larger evolution of the universe itself. In the early universe, galaxies formed rapidly and evolved quickly, building up their stellar populations and establishing their structures. In the current era, galaxies continue to form stars but more sedately, and many have settled into mature configurations. In the far future, galaxy formation will cease as the expanding universe spreads matter too thinly for new gravitational collapses to occur. The galaxies that exist will gradually fade as their stars die and are not replaced. But this distant future is trillions of years away. For now, and for the foreseeable future, galaxies remain vibrant systems. Star formation continues, though at lower rates than in the past. Galaxies merge and interact, transforming themselves in violent collisions that reshape their structures. New observations reveal galaxies at ever greater distances, showing us how they looked when the universe was young, allowing us to piece together the story of how galaxies live and die, how they transform over cosmic time, and how the universe itself evolves through the changes that galaxies undergo as they pass through their long but finite lifespans. How evolution would work on other worlds. Evolution is not a theory specific to Earth. It is a fundamental principle that must operate wherever life exists, as inevitable as gravity or thermodynamics. The basic mechanism is elegantly simple. Organisms that are better suited to their environment tend to survive and reproduce more successfully than those less well suited, passing their advantageous traits to offspring. Over countless generations, this process of natural selection shapes organisms to fit their environments with remarkable precision. Charles Darwin recognized this principle in the 19th century by studying finches on the Galapagos Islands and countless other organisms, but the principle extends far beyond Earth. On any world where life emerges, evolution would be the engine driving biological diversity and adaptation, though the specific outcomes would be shaped by each world's unique conditions. The fundamental requirements for evolution are remarkably minimal. Life must be able to reproduce, creating offspring. There must be variation among individuals. No two organisms are exactly alike. Some of this variation must be heritable, passed from parents to offspring, and there must be differential survival and reproduction. Some variants survive and reproduce more successfully than others. These conditions create evolution automatically, inevitably, as surely as releasing a ball on a slope causes it to roll downhill. Any replicating system with heritable variation and selection will evolve, whether it's based on DNA, some other information storage molecule, or even non-biological replicating systems. On Earth, DNA serves as the information storage medium for nearly all life. The DNA molecule consists of two strands wrapped around each other in a double helix, with each strand composed of a sugar phosphate backbone and a sequence of 4 bases: adenine, thymine, guanine, and cytosine. The sequence of these bases encodes genetic information, and this information is copied when cells divide, passed to offspring when organisms reproduce. Mutations, random changes in the DNA sequence caused by copying errors, radiation, chemical damage, or other factors, create the variation upon which natural selection acts. But DNA is not the only possible genetic molecule. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information and be copied, yet use different sugars or even different backbone structures than natural DNA and RNA. These artificial genetic molecules demonstrate that information storage and heredity don't require DNA specifically. An alien organism might use a completely different molecule to store genetic information, perhaps based on different chemistry more suited to its world's conditions. A very cold world might favor genetic molecules that are stable and flexible at low temperatures. A very hot world might favor molecules that resist heat degradation. The specific molecule doesn't matter. What matters is that it can store information, be copied with reasonable but imperfect fidelity, and allow variation to arise. The timescales of evolution would differ dramatically on different worlds. On Earth, bacterial generations might span minutes to hours, allowing rapid evolution. The bacteria that cause diseases evolve antibiotic resistance within years or decades as antibiotics create selection pressure, favoring resistant strains. In contrast, large organisms with long generation times evolve more slowly. Elephants with generation times of decades evolve far more slowly than bacteria. On an alien world where organisms have extremely long lifespans, perhaps living for thousands of years, evolution would proceed at a glacial pace from a human perspective, with significant changes taking millions or billions of years. Conversely, on a world where organisms reproduce very rapidly, evolution might proceed at dizzying speeds. If alien microorganisms reproduced every few minutes, like some Earth bacteria, they could evolve through thousands of generations while we watched. Such organisms might adapt to new conditions, almost in real time, developing resistance to threats or exploiting new resources faster than slower evolving species could respond. The environment determines what traits are advantageous. On Earth, giraffes evolved long necks because reaching high branches provided access to food that shorter animals couldn't exploit. Cheetahs evolved extreme speed to catch fast prey. Cacti evolved to store water and reduce surface area in desert environments. Each adaptation reflects the specific challenges and opportunities of the organism's environment. On alien worlds, different environments would favor different adaptations. On a high-gravity planet, evolution would favor short, stocky body plans with strong skeletons and powerful muscles to support body weight against stronger gravitational pull. Tall, slender organisms would be at a disadvantage because the structural demands of supporting height would be too great. Flying organisms might be rare or absent because overcoming gravity to achieve flight would require enormous energy expenditure. Over millions of generations, organisms would become increasingly adapted to moving efficiently under high gravity, perhaps developing 4 legs or even 6 or 8 for stability, with low centers of gravity and massive muscular systems. On a low-gravity world, the opposite pressures would apply. Organisms could afford to be tall and slender because less structural support is needed. Flight might be easy, favoring the evolution of wings and aerial lifestyles. Animals might leap enormous distances because the energy required to overcome gravity would be minimal. Over time, organisms might evolve increasingly delicate structures, abandoning the heavy skeletons and dense muscles necessary on higher gravity worlds in favor of lighter, more energy-efficient body plans. Atmospheric composition would profoundly influence evolution. On Earth, the transition from an oxygen-poor to an oxygen-rich atmosphere about 2.5 billion years ago, the Great Oxidation Event, was catastrophic for organisms adapted to the old atmosphere. Oxygen was toxic to them, and they retreated to oxygen-free refuges or went extinct. But for organisms that could tolerate or use oxygen, this chemical change created opportunities. Oxygen metabolism releases far more energy than anaerobic metabolism, enabling the evolution of larger, more active, more complex organisms. The size of organisms on Earth is ultimately limited by how efficiently they can deliver oxygen to their cells. On a world that never develops an oxygen-rich atmosphere, organisms might remain permanently small and metabolically limited. Without the high energy yield of oxygen metabolism, active lifestyles like those of birds, mammals, or even fish might be impossible. Life might consist entirely of small, slowly moving organisms eking out existence on the limited energy available from anaerobic metabolism. Or evolution might discover entirely different high-energy metabolic pathways based on different oxidizing agents, perhaps sulfur compounds, chlorine, or substances we haven't considered. The availability of water determines many evolutionary paths. On Earth, life originated in water, and even terrestrial organisms remain fundamentally aquatic. Our cells are filled with water, and we constantly need to replenish water lost to evaporation and excretion. On a water-rich world with extensive oceans, evolution might produce countless aquatic species, but might never develop terrestrial life if there's no advantage to leaving water. On a dry world with limited water, evolution would favour organisms that conserve water ruthlessly, perhaps evolving impermeable skins, efficient kidneys, metabolic water production, or even the ability to extract water from food or from humidity and air. Predation creates powerful selection pressures that drive evolutionary arms races. Prey evolve defences, armour, toxins, speed, camouflage, while predators evolve counter-adaptations to overcome those defences. Stronger jaws, detoxification mechanisms, greater speed, better sensory systems. This coevolution produces increasingly sophisticated organisms on both sides. On Earth, the evolution of predators coincides with the evolution of many complex features: eyes to detect prey, brains to process sensory information, and coordinate hunting strategies, complex behaviours for stalking and capturing prey. On alien worlds, predation would likely emerge wherever life becomes sufficiently complex, driving similar evolutionary arms races, but the specific adaptations would reflect the alien environment. On a world with dense fog or darkness, evolution might favour chemical or acoustic sensing over vision. On a world with three-dimensional environments, like open water or thick forests, predators might evolve better spatial perception and three-dimensional maneuverability. On a world where prey can burrow or fly, predators would evolve means to follow them into those refuges. Sexual selection, where organisms choose mates based on specific traits, creates another evolutionary force. On Earth, peacocks evolved elaborate tails, not because those tails help survival, but because peahens prefer males with impressive tails. This sexual selection can drive the evolution of traits that actually reduce survival, but increase reproductive success. On alien worlds, whatever traits the choosing sex prefers would be amplified through generations, potentially creating wildly extravagant features that serve no purpose beyond attracting mates. Convergent evolution, where unrelated organisms independently evolve similar solutions to similar problems, demonstrates that certain designs work well for certain challenges. Eyes evolved independently many times on Earth because detecting light provides such valuable information that natural selection repeatedly favoured organisms with improved light-sensing abilities. Wings evolved independently in insects, birds, bats, and pterosaurs because flight provides such significant advantages that multiple lineages evolved aerial capabilities. On alien worlds, convergent evolution would operate similarly. Any organism that needs to move quickly through water would likely evolve a streamlined body shape, because physics dictates that this shape minimizes drag. Any organism that needs to see would likely evolve some structure that focuses light onto photosensitive cells, though the specific implementation might differ. Any organism that needs to manipulate objects would likely evolve some form of grasping appendages. The specific details would vary. Alien hands might have 3 fingers or 7, might be at the end of tentacles or rigid arms, might use suction or hooks instead of friction, but the basic function of grasping would emerge wherever it provides advantage. However, historical contingency, the accidents of evolutionary history, also plays a crucial role. Vertebrates on Earth have 4 limbs because that's what the early fish that first crawled onto land happened to have. There's nothing inevitable about the number 4. If a 6-limbed fish had been the first successful land colonizer, terrestrial vertebrates might all have 6 limbs today. On alien worlds, Similar historical accidents would lock in features that become constraints on all future evolution. An early successful body plan might dominate an entire planet's evolutionary tree, with all descendants constrained by that ancestral architecture. Mass extinctions reset evolutionary trajectories. On Earth, the asteroid impact 66 million years ago that killed the non-avian dinosaurs allowed mammals, previously small nocturnal creatures, to diversify into the enormous variety we see today. Without that extinction, mammals might have remained small and marginal while dinosaurs continued dominating. On alien worlds, whatever catastrophes occur, asteroid impacts, volcanic eruptions, climate changes, nearby supernova, would similarly reset evolution, wiping out dominant groups and allowing previously marginal organisms to radiate into newly available ecological roles. The speed of environmental change influences evolutionary dynamics. Rapidly changing environments favour organisms with short generation times and high mutation rates that can adapt quickly. Stable environments favour organisms optimised for efficiency in unchanging conditions. An alien world with a highly variable climate, perhaps due to an eccentric orbit or an unstable star, would see evolution favouring adaptable generalists. A world with stable conditions for billions of years might produce highly specialised organisms, exquisitely adapted to narrow niches, but unable to cope with change. Intelligence itself is an evolutionary adaptation that emerged on Earth because it provided survival and reproductive advantages. Brains require enormous energy. Human brains consume about 20% of our total energy, despite being only 2% of body mass. This high cost means intelligence only evolves when its benefits outweigh its costs. On Earth, intelligence apparently provided sufficient advantage through tool use, social cooperation, and problem solving to justify the expense. On alien worlds, whether intelligence evolves depends on whether similar advantages exist. Some environments might favour intelligence more strongly than Earth did. A highly variable environment where adaptability is crucial might select strongly for intelligence and behavioural flexibility. A world where organisms compete primarily through social manipulation rather than physical prowess might favour intelligence. Conversely, some worlds might never produce intelligence because simpler solutions always work well enough. If food is always abundant and predators are absent, the energy costs of maintaining a large brain might never be justified. How evolution would work on other worlds follows the same fundamental principles that operate on Earth: variation, heredity, and selection, but expresses those principles through the unique circumstances of each world. A high-gravity planet would sculpt short, powerful organisms. A dark world might favour chemical sensing over vision. A frigid world might produce organisms with anti-freeze biochemistry and slow metabolisms. Each world would develop its own evolutionary history, branching from simple origins into complexity through billions of years of selection, extinction, radiation, and adaptation, creating ecosystems and organisms as unique as fingerprints, yet fundamentally related through the universal principles of evolution that must operate wherever life exists, proving that while life-specific forms might be infinitely varied across the cosmos, the process that shapes life, evolution through natural selection, remains constant, an inevitable consequence of imperfect replication and limited resources operating across deep time on any world that hosts living things. How aliens could breathe. Different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, It would necessarily be adapted to breathe this nitrogen-methane atmosphere and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. How black holes warp time itself. Time is not the constant, uniform flow that our everyday experience suggests. It can stretch, compress, and slow down, depending on the gravitational environment you're in. Nowhere is this more extreme than near a black hole, where gravity becomes so intense that time itself warps, in ways that challenge our intuition and transform our understanding of reality. Understanding how black holes affect time means grappling with one of the most profound insights of modern physics, that space and time are not separate, fixed stages on which events unfold, but rather a unified fabric that can be bent, twisted, and stretched by the presence of mass and energy. The foundation for understanding time dilation near black holes comes from Albert Einstein's general theory of relativity, published in 1915. Einstein proposed that what we perceive as gravity is actually the curvature of spacetime caused by mass and energy. Massive objects create depressions in the fabric of spacetime, much like a bowling ball placed on a stretched rubber sheet creates a depression that affects how nearby marbles roll. This curvature affects not just the paths that objects follow through space, but also the rate at which time passes. The basic principle is that time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been confirmed through countless experiments. Atomic clocks placed at different altitudes on Earth tick at measurably different rates. Clocks at sea level run slightly slower than clocks on mountaintops, because they're deeper in Earth's gravitational well. The difference is tiny, only nanoseconds per day, but it's real and measurable. GPS satellites must account for this effect. Without corrections for gravitational time dilation, GPS coordinates would drift by several kilometers per day. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers, one hovering far from a black hole in weak gravity, the other hovering closer to the black hole, where gravity is much stronger. If both observers synchronize their watches and then separate, the watch closer to the black hole will tick more slowly from the distant observer's perspective. This isn't an illusion or a malfunction of the watch. Time genuinely passes more slowly in the stronger gravitational field. The closer you get to a black hole, the more severe this effect becomes. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most counterintuitive aspects of black holes. If you were to watch someone fall toward a black hole while you remained safely far away, you would see something strange. As the falling person approached the event horizon, they would appear to slow down. Their movements would become sluggish, their signals would take longer to reach you, and their image would become increasingly red-shifted as the light they emit is stretched by the intense gravity. From your distant vantage point, the falling person would never quite seem to cross the event horizon. They would appear to freeze at the boundary, becoming dimmer and redder until they faded from view entirely. This isn't because they stopped falling. From their own perspective, they would cross the event horizon and continue falling inward in a finite amount of time, experiencing nothing unusual at that precise moment. The difference is entirely due to how time flows differently in different gravitational fields. This discrepancy between what the falling observer experiences and what the distant observer sees is one of the most mind-bending aspects of general relativity. Both perspectives are equally valid. The falling observer crosses the event horizon in, say, 10 seconds by their clock, but from the distant observer's perspective, watching that crossing would take infinite time. It would never be complete. This isn't a contradiction, but rather a demonstration that time is not absolute. Different observers in different gravitational fields experience time at different rates. The mathematics describing this time dilation near black holes was first worked out by Carl Schwarzschild in 1916, just months after Einstein published General Relativity. Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a non-rotating, spherically symmetric mass, what we now call a Schwarzschild black hole. His solution showed that time dilation increases as you approach the event horizon, located at what's now called the Schwarzschild radius, reaching infinite dilation exactly at the horizon. For a rotating black hole, described by the Kerr solution, found by Roy Kerr in 1963, the situation becomes even more complex. Rotation creates additional effects beyond simple time dilation. The black hole drags spacetime around with it in a process called frame dragging. Close to a rotating black hole, space itself is pulled around in the direction of rotation. You couldn't remain stationary, even if you wanted to. You'd be forced to rotate with the spacetime itself. This creates regions like the ergosphere outside the event horizon, where frame dragging is so strong that everything must move in the direction of the black hole's rotation. The warping of time near black holes has practical implications for anything orbiting or falling toward them. Consider material in an accretion disk spiraling into a black hole. Material in the inner portions of the disk, closer to the black hole, experiences stronger time dilation than material farther out. From the perspective of an observer far from the black hole, processes in the inner disk appear to run in slow motion compared to processes in the outer disk. This affects how we observe black holes and interpret the light we receive from matter near them. Time dilation also affects the gravitational redshift of light, escaping from near a black hole. Light climbing out of a gravitational well loses energy, its wavelength stretching toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation. They're two aspects of the same phenomenon. A photon emitted from close to the event horizon will be dramatically redshifted by the time it reaches a distant observer. If the photon is emitted from the event horizon itself, it would be redshifted infinitely, its energy dropping to zero, another way of understanding why nothing can escape from beyond the horizon. Inside the event horizon, the warping of spacetime becomes even more extreme. In this region, the roles of space and time actually exchange in a sense. Outside the horizon, moving forward in time is inevitable. You cannot choose to move backward in time, but you can choose your direction in space. Inside the horizon, moving toward the singularity at the center becomes as inevitable as moving forward in time outside the horizon. All possible paths lead inward, and reaching the singularity becomes as unavoidable as reaching the next moment in time. The singularity at the center of a black hole represents a place where space-time curvature becomes infinite, and general relativity's equations break down. At the singularity, time itself becomes undefined in the classical sense. This suggests that general relativity is incomplete, that a theory of quantum gravity would be needed to properly describe what happens at and beyond the singularity. String theory, loop quantum gravity, and other approaches to quantum gravity propose different solutions to what occurs at this extreme limit, but none have been confirmed experimentally. Supermassive black holes at the centers of galaxies create fascinating time dilation effects on galactic scales. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, contains about 4 million solar masses. Stars orbiting close to this black hole experience measurable time dilation. A star in a close orbit around Sagittarius A star, coming within a few hundred times the black hole's event horizon radius, would experience time flowing noticeably slower than we experience it here on Earth, 26,000 light-years away. Precise measurements of these stars' orbits by Andrea Ghez and Reinhard Genzel, who shared the 2020 Nobel Prize in Physics for this work, have confirmed general relativity's predictions in this strong gravity regime. Time dilation near black holes has captured popular imagination, featuring prominently in science fiction. The film Interstellar depicted a planet orbiting close to a massive rotating black hole, where time dilation was so extreme that 1 hour on the planet's surface equaled 7 years of time passing elsewhere. While Hollywood took some liberties, the basic physics was sound. Physicist Kip Thorne served as scientific consultant and later published papers about the black hole physics portrayed in the film. Such extreme time dilation is theoretically possible near a rapidly rotating supermassive black hole. Binary black hole systems, where two black holes orbit each other before merging, create incredibly complex spacetime geometries. Each black hole warps time in its vicinity, and the combined warping creates regions where time flows at different rates depending on your location relative to the two black holes. As the black holes spiral together and merge, events that produce the gravitational waves detected by LIGO and other observatories, the warping of spacetime becomes dynamical, with gravitational waves carrying information about how spacetime is oscillating and rippling during this violent event. The connection between time dilation and energy offers another perspective on these phenomena. According to general relativity, gravitational fields contain energy. A clock deep in a gravitational well, where time runs slowly, can be thought of as having less energy than a clock far from any gravitational source. The gravitational redshift of light, the loss of energy as light climbs out of a gravitational well, reflects this energy difference between different regions of curved spacetime. Black holes also raise profound questions about the nature of time itself. Some interpretations of quantum mechanics and general relativity suggest that time might not be fundamental, but rather an emergent property of more basic physical processes. Black holes, where classical notions of time break down at the singularity, might provide clues about the true nature of time. The information paradox, the question of what happens to information that falls into a black hole, connects to deep questions about time, entropy, and the quantum nature of space-time. Hawking radiation, predicted by Stephen Hawking in 1974, introduces another connection between black holes and time. Quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate over extremely long timescales. This process involves virtual particle pairs appearing near the horizon, with one particle falling in while the other escapes. The evaporation means black holes have a finite lifetime, and it connects quantum mechanics, gravity, and thermodynamics in ways that hint at a deeper theory unifying these domains. The warping of time near black holes is not science fiction, but established physics, confirmed through observations and experiments. Every time LIGO detects gravitational waves from merging black holes, it's detecting ripples in spacetime that carry information about how dramatically spacetime, and therefore time itself, was warped during the merger. Every observation of matter orbiting near black holes, every measurement of gravitational redshift, every test of general relativity in strong gravitational fields, confirms that time is not absolute, but is woven into the fabric of spacetime, susceptible to warping and stretching by mass and energy, reaching its most extreme manifestation near black holes, where the flow of time slows to a crawl, and ultimately, at the event horizon, appears to stop entirely from the perspective of distant observers watching the inexorable pull of gravity on the fabric of reality itself. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system, when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometer and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbit would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into two or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other, They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The Near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common center of mass. The asteroid Sylvia, about 260 kilometers in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometers from Sylvia, with an orbital period of 3.6 days. Remus orbits closer at about 710 kilometers, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometer-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How fast you'd need to go to leave a planet. Every object massive enough to have significant gravity holds onto anything near its surface. A ball thrown upward eventually falls back down. A bird must constantly flap its wings to stay aloft. Even the fastest jet aircraft cannot fly into space. Eventually it runs out of altitude and must descend. To truly leave a planet, to escape its gravitational grip entirely and coast into space without using any more fuel, you must reach a specific speed called escape velocity. This critical speed depends on the planet's mass and size, and understanding it reveals why launching rockets is so difficult, why some worlds can hold atmospheres while others cannot, and why the smallest push can send an astronaut drifting away from an asteroid while escaping Earth requires enormous rockets burning millions of pounds of fuel. Escape velocity is not about reaching a particular altitude or getting above the atmosphere. It's about speed, specifically moving fast enough that your kinetic energy equals or exceeds the gravitational potential energy binding you to the planet. If you launch something straight up at exactly escape velocity, it will climb higher and higher, slowing down continuously as gravity pulls it back, but never quite stopping. It will coast to infinite distance, arriving there with zero velocity, having converted all its initial kinetic energy into potential energy. Launch at any speed less than escape velocity, and gravity eventually wins, pulling the object back down. For Earth, escape velocity at the surface is about 11 kilometers per second, roughly 40,000 kilometers per hour, or about 25,000 miles per hour. This is more than 30 times faster than a typical passenger jet flies. To reach this speed, starting from rest requires enormous amounts of energy, which is why rockets are so large and burn so much fuel. The Saturn V rocket that launched Apollo missions to the Moon stood over 100 meters tall and weighed more than 2,000 tons at launch. But only about 50 tons of that mass, less than 3%, was the actual Apollo spacecraft and crew. Everything else was fuel and engines needed to accelerate that relatively small payload to the speeds necessary for spaceflight. Escape velocity depends on two factors: the planet's mass and its radius. More massive planets have higher escape velocities because stronger gravity pulls harder, requiring more speed to escape. Larger planets, meaning planets with larger radii, have lower escape velocities at their surfaces because you start farther from the center of mass where gravity is weaker. Earth is more massive than Mars, but also larger, and the combination means Earth's escape velocity is about 4.5 kilometers per second, higher than Mars's escape velocity of roughly 5 kilometers per second. This makes Mars somewhat easier to launch from than Earth. A rocket leaving Mars needs to reach only about half the speed required to leave Earth, which translates to roughly 1/4 the energy. Energy requirements scale with the square of velocity. Mars's thinner atmosphere also helps, creating less air resistance during ascent. These factors make Mars an attractive location for future space missions that might launch from the surface to explore the outer solar system or return to Earth. The Moon, much smaller and less massive than Earth, has an escape velocity of only about 2.5 kilometers per second, less than 1/4 Earth's escape velocity. This made the Apollo lunar module's ascent from the Moon's surface relatively straightforward compared to launching from Earth. The ascent stage needed far less fuel and could use a much smaller engine. The low escape velocity also meant that the lunar module could take off without the massive multi-stage rockets required for Earth launch, using a single engine to reach lunar orbit directly. Jupiter, the most massive planet in our solar system, has an escape velocity from its cloud tops of about 60 kilometers per second, more than 5 times Earth's escape velocity. Launching from Jupiter, if there were a solid surface to launch from, would require vastly more energy than launching from Earth. Any spacecraft falling into Jupiter's atmosphere would need extraordinary speeds to escape again, which is why missions to Jupiter use gravity assists from other planets to gain speed rather than attempting to enter and exit Jupiter's deep gravity well. The concept of escape velocity explains why planets can hold atmospheres, while asteroids and comets cannot. Gas molecules in an atmosphere move at speeds related to temperature. Hotter gases move faster. For an atmosphere to remain bound to a body over billions of years, the typical speed of atmospheric molecules must be significantly lower than escape velocity. If molecules regularly reach speeds close to or exceeding escape velocity through random thermal motion, they leak away into space. Earth's atmosphere consists primarily of nitrogen and oxygen molecules that move at average speeds of a few hundred meters per second at normal temperatures, well below escape velocity. The lightest element, hydrogen, moves much faster at the same temperature because lighter molecules move faster for a given thermal energy. Hydrogen molecules at Earth's atmospheric temperature move at average speeds around 2 kilometers per second, which is still well below escape velocity, but close enough that over billions of years, Earth has lost most of its primordial hydrogen. The Moon's escape velocity is low enough that essentially no gas can remain in a lunar atmosphere. Any molecules would need to be extremely cold to have velocities below escape velocity, but solar heating warms the lunar surface during the long lunar day, giving molecules enough energy to escape. This is why the Moon has no atmosphere. Its weak gravity cannot hold even the lightest gases against thermal evaporation. Mars, with escape velocity between the Moon's and Earth's, represents an intermediate case. Mars can hold heavier molecules, like carbon dioxide in its atmosphere, but it loses lighter molecules more easily. Mars also lacks a strong magnetic field to protect its atmosphere from the solar wind, the stream of charged particles from the Sun. Over billions of years, the solar wind has stripped away most of Mars's original atmosphere, leaving the thin atmosphere we observe today. Escape velocity decreases with altitude. At the surface, you need to reach Earth's full escape velocity of 11 kilometers per second. But at the altitude where the International Space Station orbits, about 400 kilometers up, escape velocity is slightly less, around 10.9 kilometers per second. The difference is small because 400 kilometers is not much compared to Earth's radius of about 6,400 kilometers. But at lunar distance, about 380,000 kilometers, escape velocity from Earth has dropped to only about 1 kilometer per second. Apollo spacecraft needed to reach only this lower speed to escape Earth's gravity after coasting most of the way to the Moon. Escape velocity is the same in all directions. You could launch straight, up, horizontally, or at any angle, and you'd need the same speed to escape. The direction doesn't matter for escape, only the speed. However, in practice, rockets don't launch straight up. They curve their trajectory to gain horizontal velocity as well as altitude, because horizontal velocity is what's needed for orbit. Reaching escape velocity while moving horizontally means you escape while also having momentum that carries you away from the planet, rather than climbing straight up until you barely escape with zero velocity. Black holes represent the extreme case of escape velocity. At the event horizon, the boundary of a black hole, escape velocity equals the speed of light. Nothing can move faster than light, so nothing can escape from within the event horizon. This is what makes a black hole black. Not even light can escape once it crosses this boundary. For a black hole with a few times the Sun's mass, the event horizon has a radius of only about 10 kilometers. The extreme compression of mass into such a small radius creates escape velocities that reach and exceed the cosmic speed limit. Interestingly, you don't have to reach escape velocity to get into space. Rockets reaching orbit around Earth need to achieve only about 8 kilometers per second at orbital altitude, less than escape velocity. Orbital velocity is the speed at which your sideways motion exactly balances gravitational pull, so you continuously fall around the planet rather than falling back to it. This is easier to achieve than escape velocity, which is why orbital missions are more common than interplanetary missions. The Space Shuttle, for example, accelerated to about 8 kilometers per second to reach low Earth orbit, then used additional fuel to accelerate to higher speeds only when needed for missions to higher orbits or to the International Space Station. Missions leaving Earth orbit for the Moon, Mars, or other destinations required additional speed beyond orbital velocity to reach escape velocity and break free of Earth's gravity. Understanding escape velocity also explains how gravity assists work. When a spacecraft flies past a planet on a carefully calculated trajectory, it can gain speed by essentially stealing a tiny amount of the planet's orbital momentum. From the spacecraft's perspective, it falls toward the planet, swings around it, and flies away. If the trajectory is chosen correctly, the spacecraft leaves moving faster relative to the Sun than it arrived, having been accelerated by the planet's gravity without burning any fuel. The Voyager spacecraft used multiple gravity assists from Jupiter and Saturn to reach speeds high enough to eventually escape the solar system entirely, crossing into interstellar space decades after launch. Calculating how fast you'd need to go to leave a planet comes down to a simple formula involving the planet's mass and radius, derived from Newton's law of universal gravitation. The energy required to escape grows with planetary mass and shrinks with planetary radius, creating the variety of escape velocities we observe throughout the solar system. From tiny asteroids where you could literally jump into space if you weren't careful, to massive Jupiter where even the most powerful rockets would struggle to escape, the speed required to leave a world tells us about that world's fundamental properties and shapes everything from how we design spacecraft to which worlds can hold atmospheres, determining the accessibility of each destination in our cosmic neighborhood and beyond.